All right, awesome. Um, you can go ahead and go to the next slide, Linden. You can start whenever you're ready, Emily.
Awesome. So yeah, thank you all for coming. My name is Emily Feuerborn, and my partners are Linden Van Hoose, Logan Rodriguez, and our project manager is Esteban Lopez. Today we're going to be looking at Gerdau's continuous casting process. Gerdau has been our industry partner this past year. Our main points of contact have been Clinton Johnson, the management systems facilitator, Eric Springs, the QA and metallurgy manager, and Alan Doss, the quality labs routine facilitator. So specifically, we're going to be diving into the transition phase of the process of casting at Gerdau. And the objective of our project is to create a model that the transition technician can then use to better predict the amount of transition steel that needs to be removed during the casting process. So Gerdau was founded in Brazil, starting as a nail factory in 1901. And after growing for 45 years, it expanded into a steel making manufacturing company. So in 1981, Gerdau expanded internationally, and in 1989, it expanded into North America. So they now have 10 steel mills in the US and 3 in Canada that specialize in long steel and special steel production. So our project is going to be focusing on this Fort Smith mill, which produces the special steel products. And these are mostly used for transportation and energy applications such as automobiles and large vehicles. So as I mentioned earlier, Gerdau uses a continuous manufacturing process, and we were actually able to witness this process firsthand when we took a trip to Fort Smith and got to tour the mill there, thanks to our main point of contact, Clinton Johnson. So we spoke to several technicians there and gained a better understanding of our system of interest. So we actually learned that the mill uses only recycled steel, which they sort by chemistry in the scrapyard. And then that steel is brought into the electric arc furnace, or the EAF, where it's melted. And you can see that in the first photo on this slide. The molten steel is then transferred to a ladle where slag is applied to avoid oxidation, and then alloys are added based on the customer specifications of the order. The ladle then moves to a vacuum, which is shown in the second photo, to help eliminate other gases entering the steel. And the steel is then brought to picture 3, which is the rotary casting station, where the steel is poured into a tun dish to reduce the occurrence of impurities. And then from the tun dish, the liquid's poured into a rotating caster. At the end of casting, the billets are cooled, and then they move to the transition phase. So because Gerdau uses a continuous manufacturing process, there's no parts of the billets, or there are parts of the billets produced that need to be cut out because the steel is mixed with 2 different grades of chemistry. So this is primarily what we're going to be focusing on. The transition technicians use different parameters to determine how much to cut, but no part of their process is automated. But you're going to hear more about that in a little bit. So finally, after the billets have been cut, they then enter the reheat furnace and begin the rolling process. So the billets pass through the rolling mill, which is shown in the 4th picture, to achieve the desired size specifications of the order. And then they're cooled once again, and they are bundled up so that they can be delivered to the customer, which is shown in the 5th and final photo.
So the steel orders come into Gerdau at different specified grades. Each order has a specific range of alloy metal chemistries that must be met. All alloy elements in the steel order have a specified aim as well as an acceptable minimum and maximum composition. The change in element composition between grades is induced by melting scrap of the correct chemical makeup until each element lands inside that acceptable range. Because the manufacturing process is continuous, there is a certain amount of unusable steel between orders that does not meet either chemistry specification. This steel has an undesirable chemistry makeup. This is referred to as the transition metal. To better understand the idea of the transition metal, compare the process to making Doritos. If the Dorito manufacturing facility was a continuous process, you are bound to get some weird flavored Doritos when you switch from nacho cheese to Cool Ranch. This is what the transition steel is. It's the in-between metal. The total weight of transition metal that is cut is determined by an array of different factors. The most significant of these is the difference in chemistry between orders. The element that requires the most significant change in chemistry is known as the transition element. Transition weight can be estimated by identifying the transition element and utilizing a set of guidelines that predict the weight. These guidelines take into account various parameters such as mold size, tonnage size, and temperature requirements. With the transition element weight and the parameters, technicians are able to make an estimation of how much to cut. Transition steel is then cut out and a sample is taken to a spectrometer to be tested. If the end of the transition meets the new order's chemistry specifications, no more cutting is required and the steel batch can begin further processing. The goal is to reduce the amount of usable steel included in the transition to a minimum. However, the current system of estimating transition metal is inconsistent as the technicians don't have an automated way to calculate how much to cut. Between the grade demands, the guided logic, and the spectrometer, the technicians are estimating in different ways. More experienced technicians may not even use the guided logic and just lean on cutting more than necessary. As a transition steel is estimated and cut, there are two general outcomes, overcutting and undercutting. If the transition is undercut, the batch of steel does not yet meet the required chemistry for that order grade. The technician must halt the entire manufacturing process to recut the transition metal until the correct chemistry is reached. This creates not only a delay in the process and delay of delivery, but also a quality control issue that cannot be ignored. Again, imagine buying a bag of Doritos that is supposed to be Cool Ranch and they tasted nothing like Cool Ranch. If the steel is overcut, however, the transition contains some amount of usable steel. This steel must be scrapped and recycled back into the system. Overall, all transition metal once cut is then scrapped and recycled through the system.
All right, so furthermore, talking about the transition process, we were able to identify some of the factors that would affect the transition estimation error. So we divided all of these factors into 4 principal branches. And as you can see on the fishbone diagram, going first onto the first branch, which is material, here we have all of the material or chemical factors that would affect the transition estimation error. So for example, we have the chemical composition. And as mentioned before, for example, if the first order has a chemical composition different from the second order, then there's going to be a difference, and then you're going to have the transition metal. That's also going to be part of the difference in grades, as those grades define the ideal conditions, chemical conditions of the orders, and those difference in grades are going to tell us if there's going to be a transition or not. Lastly, we also have the temperature of the metal, which is going to go through all of this process, which is also going to affect the transition error. Going to the next branch, I'm going to talk about the equipment. So for equipment, these are going to be all of the equipment parts or machines that are being utilized to obtain the metal, and which are going to affect the transition estimation error. So for example, here we have the tonnage size. As Emily mentioned before on the, I think, second slide, we were able to see that the steel is poured into the tonnage, which later goes to the casting process. For the tonnage size, we have two different sizes of boxes. We have a small tonnage size box and a big one. That's going to affect the drain height, as you can see. So one of the other factors, and the drain height is going to tells us at what point you're going to cut and how much metal is going to be left in the tonnage. So that's also going to end up affecting the transition amount. Also, we have the mold size. So depending on the order, we're going to have different mold sizes, and that's going to end up affecting the speed at which the metal is going to come out of the tonnage. Also, we have the number of strands. This is going to be the number of outputs that are going to come out of the tonnage. So we have up to 3 number of strands, but sometimes they can utilize just 2 or just 1, depending on the amount of speed or the amount of time at which they wanted to get that done. Lastly, for this branch, we have the spectrometer, which is the machine that they use to test and see the chemical composition of the metal after the cutting process. Then going to the other branch, you have personnel. So this is going to be mostly experience training that each transition technician gets. So based on experience or their training or what method they utilize, that's going to affect their mental thinking process, and that's going to end up affecting the amount of steel that they're going to want to cut. Lastly, going on to the last branch, we have the model. So previously, Gerdau used to have a linear model that they would use to try to help the technicians to get an estimation for the transition weight. However, this model showed that it was very inaccurate, and at some point it stopped working as well. So right now they don't have like a Excel model or anything like that they can use, and that's where we're gonna go. And what we created 2 different models that are gonna help the transition technicians to better estimate the transition weights.
So the most important measure in evaluating our system performance is the difference between the actual weight of the transition and the technician's estimated weight, which is the estimation error. Now it's important to note here that the data obtained for actual weight is the amount of total scrap actually cut for that transition, not the exact weight of the transition metal itself. This means that the actual weight will always contain some good amount of steel that causes a certain degree of inaccuracy for our analysis. The degree of error is unknown, as Gerdau currently does not have a process in place to actually take this measurement. But at the end of a transition, technicians log all relevant transition data, including date, grade, technician, and weights. And these parameters can be analyzed to determine their effect on estimation error. So 2018-2019 transition data was used to conduct all of our analysis. And to ensure analysis accuracy, the data was cleaned as it became quite obvious that much of the data contained technician input error. And additionally, many data points were missing information, like most notably, estimation weight was not entered for a large amount of data. Weight difference distribution analysis was conducted to serve as a baseline for system performance. It should be noted that our objective is to decrease the weight of transition scrap produced per individual transition, not to decrease the number of transitions themselves. So our cost analysis will therefore be determined by assessing the average transition weight rather than total transition scrap produced. So analyzing our transition weight distribution, can be seen that the weight follows a positively skewed distribution, with the mean hovering somewhere around 12,400 pounds. After conducting an Anderson-Darling test, we found that the transition weight actually does not follow a normal distribution. So this most likely indicates functions in the system that they use to schedule the smallest possible transition element change between batches. The distribution parameters will serve as a baseline for other analysis. Interestingly, estimated weight difference, which is that actual weight minus the estimated weight, also follows a positively skewed distribution. This is most likely due to a few different factors. Most importantly, it's evident that the current estimation model is far more averse to the risk of undercutting than it is to overcutting. You can see in the distribution of weight difference that the majority of observations fall in a region of slight overestimation, and subsequent observations tail off towards higher ends of overestimation. So of all of our observations, overestimation occurred actually about 85% of the time. So on average, technicians overestimated transition weight by about 2,500 pounds. In addition, much of the skew can be attributed to human error, in which there's miscalculations in the transition element that could cause for larger amounts of transition metal to be produced. Due to the lack of normality, we conducted a Box-Cox transformation in order to create more viable analysis. Variance analysis was conducted on transition technicians to evaluate the best performers. So our technicians with low variances, such as technician JP, as you can see on the screen there, indicate higher tendency for the initial estimation to be closer to their final transition cut. So we took two approaches in creating our model, multiple linear regression and a machine learning random forest technique. So we considered several predictors, including mold size, absolute transition element weight, drain height, number of strands, whether the transition element was losing or gaining, and then the transition element itself. We also added some parameters artificially. For example, that lose gain there is a binary variable we added. So we tested all of our predictors for significance in the interest of creating our most accurate models. And as you can see, after a lot of testing, we decided to land on these three predictors here: absolute transition element weight, drain height, and transition element. As you can see here, mold size also has a very low p-value, which indicates it might be a good predictor. However, we had to leave it out just due to the fact that it didn't have a high enough sample size, and to maintain our sample size and the accuracy of our models, we had to leave it out of our model. Number of strands and lose or gain, those prove that they're fairly insignificant in our transition estimation. So we left those out as well. And we landed on these three predictors here. And so we landed on 5 elements that we're using to create our models. Each one is going to have an individual model for multiple linear regression. These 5 elements are included just because these are the most common elements that occurred as the transition element. So these elements had the most data, and these were the ones that we were able to create our models off of. There are more elements in this that can be transition elements, but there's simply not enough data to create a viable model for them. So for each model, we randomly split the data into training and testing sets. We generated our models from our training sets, and then we conducted residual analysis to ensure the goodness of fit for our models. So our best 3 models were for chromium, manganese, and nickel, and as you can see, they have much higher R² values, indicating a better model. So that's the case that they have so much higher R² than the other 2, mainly due to the fact that we had the most amount of data for those. As you can see, carbon and silicon, much lower R² values, but that's simply just because there was a severe lack of data. So then we went ahead and calculated the mean squared error for each model by comparing the predictions from our training set to the actual values from our testing set, and we are able to assess the accuracy that way. So it's important to know that the model is intended to be a jumping off point for the technicians. There are so many uncontrolled variables that occur during transitions that technicians often have to make adjustments on the fly. For this reason, the model estimations are meant to serve as a starting point, and one that will likely need to be adjusted as issues occur on the manufacturing floor.
All right, so now talking about the random forest model, we were able to, well, first of all, before creating this model, we had a meeting with Dr. Chimke, as mentioned before, to talk about some modeling techniques. That's where we started working on a multiple linear regression model, and he advised us to meet with Dr. Liu to see if we can use a machine learning technique as well for predicting our estimation. So for predicting our estimates. So after meeting with Dr. Liu, we decided to go ahead and create a random forest model. We had to learn all about random forests and get to know how to create those in RStudio. We used RStudio to create random forests. So basically, I would say the major differences between this one and the multiple linear regression is that in this model, we were able to utilize all of our predictors. So we use number of strands, mold size, transition element weight, whether we're losing or gaining weight, drain height, and transition elements. This was easier to do on the random forest model since random forest handles the lack of data very well, and more data can be added, and the random forest is going to adjust with data and improve itself. So one of the changes that we had to make these random forests work is, for example, in our data, we had some categorical factors. So for example, the transition element, we have carbon, nickel, silicon, and in our data it says C for carbon or Ni for nickel. So in order to make it work on a random forest, we had to change those values into numbers. So instead of having C for carbon, we're going to have a 0. Or for nickel, we're going to have a 1 and 2 for another element. So that way we were able to include it into our data and make it work into our model. As mentioned before, we used training and testing sets to test our models. We used a ratio of 75 to 25 to work on these 2 models. So yeah. All right. So also in order for us to compare and see the major difference between our 2 models and Gerdau's model, as mentioned before, Gerdau used to have a model that they stopped using due to its lack of accuracy, and it stopped working at some point. So as you can see on the table, you can see the random forest. It's at the top since it has the best value for that estimation, for the estimation. So for MSE. So in comparison to the multiple linear regression, if we were able to remove those 2 elements that weren't as accurate, then the multiple linear regression would be very similar to the random forest and even a little better. But again, that's also going to change as Gerdau can get more data. They'll be able to improve the random forest estimations and also create better multiple linear regression estimates.
So like we've mentioned, along with the implementation of the models, we were hoping to create some sort of tool to help standardize the way the technicians log the data. And then hopefully, along with that, for future analysis and future modeling, they can have a larger sample set so they can have a more specific model and gain more transition elements with their MLRs in the future. And so this is the start of the tool. So basically when the transition technician logs on to log their transition, they'll start with this Excel sheet and then they'll see the welcome screen. And so we have 4 buttons here. The first one is purely instructional. Second one is to log the data. The third one is for future maintenance of the tool. And then the last one is for anything post-transition. And so we'll go through each of those buttons so you can see the details of the tool. So like I said, the first one is purely instructional. So ultimately when they just click this button, 3 different message boxes will come up and it'll kind of guide them how with each button and when to click the button and what to do and what it's used for. And then where to find also results from each transition. Then the second button is a little bit more meatier. It's the record transition detail button. And so when they click that, they'll see the user form in the bottom left corner, where it'll basically have all the parameters we've just talked about to log for their use. So most of them are in list boxes. This is just for the kind of issue that we faced where we had a lot of missing data points, whether it was with ton dish size or whether it was with mold size. And these could be really great parameters for the future. But because of the small sample set, we weren't able to use them as parameters for our models. And so basically the technician will come in here, fill all of this out, and then it will lead them to 2 different sheets. The first one will be the estimation results based on what they just inputted. And so this is coming from the transition element that it finds from those melt practices. And then it'll also come from the other parameters that we talked about, the other predictors that we talked about earlier. And so the first sheet that'll take them immediately to is the estimation results sheet. And so this will show the heat from and the heat to, and then their estimation weight based on the guidelines. And these guidelines that we used to find this was actually from their most experienced technician, Terry Fisher. And so he took us through multiple times, basically how he goes through a transition and how he calculates it in his head, and then based on the transition element weight. And so we implemented his guidelines into the code. And so it'll output that weight, and then it will also output the regression model weight based on the transition element in the MLR model. And then with that, it'll output the feet below and the total feet. And this is for the cutting purposes. So the technician will be in their office making the cut or making the decision, and then go to the command or control room and see kind of exactly what's going on, come in with this suggestion of how many feet below and total feet to cut. And then we also have a note section. And so that note section is basically for if there's not a transition, if the transition element weight is too small, there's not a transition, it'll output there in the notes part. And then also, let's say, like we said, there's only 5 transition elements, but in reality, there could be other transition elements. So if the regression model shows 0, then in that notes, it'll show why it's 0, because the regression model does not account for that transition element. And so that's just there for the technician's use and for future use when they see it on the big Excel sheet, because there's also another Excel sheet that shows all of the data that they've logged over time. And in the bottom right-hand corner, you can see the melt practice sheet. And so this is just for the kind of automation and to reduce human error in calculating. So for each transition or for each element in the chemical makeup, there's a min, a max, and an aim of that makeup. And so for carbon, for example, it shows the aim difference, which is 0. So carbon doesn't change. However, for vanadium later, you can see that there is a weight change. And so this sheet basically in the code automatically calculates, it goes through those melt practices and it calculates the weight change and whether it's losing or gaining. And then it finds the maximum weight change. And it declares that the transition element, and it outputs there. And so that, again, is just for basically reducing human error and human calculation, because right now that's manual finding that weight change. So yeah, this is just basically the big transition element and getting the estimation from the models.
So many factors can change on the manufacturing floor after the transition or while the transition is happening. And so the next button kind of takes that fact into account and allows the transition technicians to change any factors that that were altered during the transition after they have completed the transition. So this post-transition button does exactly that. The transition technician can select the heat that they were, or the heat from and heat to that they were transitioning between, and then they can change any of those 3 factors that you can see on the screen here: drain height, tonnage size, or number of strands, if those factors changed on the manufacturing floor. A cool note with this button is that if one of those factors did change and they use this tool to make that change, then on the data that it is automatically generating, it will highlight those variables in yellow. That way they have a visual cue of any data that has been changed after the transition. This button also allows the technicians to add comments to any transition. Gerdau mentioned to us that they really like to stress that the technicians be adding comments so that they can really go back through that data and see exactly what was happening during that transition. So this button allows them to do that, as well as add the actual weight of the transition. So that way the tool will automatically compare the estimate that the technician got from this tool on the front end. It will compare that to what the actual weight cut of the transition was, and all of that again will be outputted onto a sheet with clean and organized data. So the final button that we have created on this tool is the tool maintenance button. And this is just a button that simply allows the transition technicians to alter the tool if necessary. So let's say, for example, Gerdau hires a new transition technician. Well, then they can go to this tool or this button and click on the options that allow them to add a transition technician, type in their initials and click the add button, and the tool will automatically update its own database so that they don't have to go into the actual VBA code and change anything manually. So if you recall, in the bottom left corner on the very first button that Linden talked about, all of the parameters show up as list boxes, and so this tool, the tool maintenance button, will automatically change those list boxes on that first button so that it's updated with the current information that is necessary.
All right, so lastly, we wanted to talk about some of the impact that we were able to provide with this project. So basically what we did is we are comparing our two models to Gerdau's guidelines, and that's the current process that they use. So basically from the MSE, from the error, we calculated how much we would be able to save for our MLR and the random forest, as you can see on the table below. And then we multiply that by the number of transitions that we had on 2018. And that's to give an example of how much you would be able to save in a year. As also Logan mentioned before, just want to make clear that since a lot of the parameters are going to change in the current cutting process, the transition technicians need to make decisions at that moment, and that's going to affect these cost analysis values, since our models do not include any of those varying factors, that variation at the end. So at the end, the cost reduction is it's gonna be less, but nevertheless, this is what we were able to get comparing the guidelines that they currently use comparing to our model. Now, Clinton Johnson, our primary contact at Gerdau, is also gonna make some additional remarks to the cost analysis and the way they get the cost for this process. So whenever you're ready, Clinton. I don't know if he's here. Okay. Go ahead, Clinton.
Can you guys hear me?
Yes.
Good. So, we tried to calculate these savings the simplest way possible. There's a number of factors that go into this, from errors that can be handled from the operation side to making sure that we cut the steel at an optimal length for the rolling mill to get the correct number of bars out of the billet. So at the end of the day, we use just a melt shop conversion cost, which goes from anywhere from 250. I always say around $250 per ton of steel, and so that's how we kind of came up with this. Conversion cost is all the variable costs throughout this particular part of our process, which is from melting the steel down and casting the steel and all the refining steps in between. And so that includes labor, energy, maintenance costs, but it does not include the raw material. As stated earlier, when we calculate scrap savings, we don't calculate the raw material because we can just recycle the steel right back into the process. And so we just kind of went about it a simple way. The other thing will be is, as the team noted, we have to now take into consideration of how risky do we want to be, as far as we typically always overcut. And so over time, as we implement this, we'll try to be a little more risky with the help of this tool, which will hopefully show a percentage of these savings over time. Again, these savings are in a perfect world, right? And so we do the best we can. Thanks, Esteban.
Thank you, Clinton. You can go to the next slide. Thank you. All right, so finally, going again over everything that we presented. Our goal is to help the transition technicians to better estimate the transition. And to do this, we were able to create two models, multiple linear regression model and a random forest model. And also in addition to that, we were able to create an Excel tool where we also included code of the guidelines that they currently use. And also the multiple linear regression was included into that. So that's going to be able to help the transition technicians to log more data, and that's also going to provide clean data where they would be able to improve the random forest and create better multiple linear regression models later on with that clean data that's going to be provided. So lastly, as mentioned on the previous slide, we were able to provide that cost analysis that, as mentioned before, is the comparison of what they are currently using compared to our models. And as Clinton mentioned before, that's going to be based on ideal conditions. So we're not considering all of those varying factors that would change or reduce our cost because those happen at the end when the technicians have to take action at that moment. So thank you all for hearing our presentation, and we're going to be getting some questions, so feel free to ask any questions that you want. Thank you.